Okay, so making aldehydes and ketones first of all. So I'm just going to treat this as if I was revising with my own students in college. Okay, so we're just going to go through the essentials. So aldehydes and ketones, they are made by oxidizing alcohols. Okay, and the only two types of alcohols that are oxidizable are primary and secondary. Okay, tertiary alcohols aren't oxidized. Okay, so I'll just say tertiary alks, not oxidized. Explain why when we get to the end of this part of the session. Okay, just a quick reminder of what we mean by primary and secondary alcohol. Okay, so primary alcohol, there's one carbon attached to the OH carbon, the hydroxyl carbon. Okay, so for example, something like ethanol, okay, that's the hydroxyl carbon. There is one carbon directly attached to that. Okay, now I could make that carbon chain really long if I wanted to. I won't put all the hydrogens on, but okay, so if you imagine that one there, okay, that's still primary because that carbon has only got one carbon directly attached to it. So that's a primary alcohol. Now, often is the case in chemistry, there's, you know, we're bound by these rules. There's these set of rules, and then there's often an exception to the rules, which kind of messes people heads about a bit. Methanol is a primary, it's classed as a primary alcohol. Okay, and methanol is literally just CH3OH. So you can see that the OH carbon doesn't have any carbons attached to it, just hydrogen, and obviously the OH group. It's classed as primary. Okay, so that's like an exception to that rule. Okay. So primary alcohols, one carbon directly attached to the OH carbon, and secondary alcohol has two carbons attached to the OH carbon. Okay, so for example, let's just turn this into a secondary one. Let's make that the OH carbon. So let's just make these CH3 groups. Okay, so you can see straight away that there's your OH carbon, two carbons directly attached, therefore it's secondary. These carbon chains can be as long as you want, okay, just like I did before. Just make that a bit longer. Still secondary because that carbon has still only got two carbons directly attached, okay? So secondary carbon. Obviously a tertiary carbon has three carbons directly attached, okay. Right, so we make aldehydes and ketones by oxidizing alcohols, primary and secondary alcohols. So we need an oxidizing agent to do that. The oxidizing agent, which we represent in the equations as O in square brackets, typically is potassium dichromate 6, or K2Cr2O7, and it's acidified with sulfuric acid. Okay. Now, I don't know about other exam boards, but OCR are really hot on that acid there. You need to know that that's the acid used to acidify the potassium dichromate 6. Okay. Now, you could use sodium dichromate 6, as long as you've got the dichromate 6 ion, so Cr2O7 2 minus with some sulfuric acid, it's going to work. Okay, but the common one to use is acidified potassium dichromate 6. Okay, and it's worth just noting here, this chemical is orange in colour. Okay, The reaction needs heat. So you could actually do this in a test tube just with a source of heat, you know, sort of a boiling hot water bath. We sometimes do it on a test tube scale in the lab just as a quick test for a functional group. But typically you would use reflux or distillation as the heat source, and we'll come on to what happens when you use those different methods, okay? So the reaction needs heat, can be done in a test tube. Typically you would use either reflux or distillation, okay, to carry out the reaction. And I'm just going to find, I've just quickly drawn up what they look like, and we'll refer to these. Hopefully you can remember. So reflux looks like that, where your condenser's in a vertical position, and distillation, I'll use these again in a minute though, is where your condenser's on a slant, okay? So that's your distillation there, okay? Right. And the only other sort of general thing to say is the colour change. So if there is a reaction, so if it's a primary alcohol or a secondary alcohol and you've got this acidified potassium dichromate 6 and you heat it up, it will go from orange to green. And obviously, if you had a tertiary alcohol, it would stay orange, no reaction would happen, okay? So colour change is orange to green. And one of the most common mistakes I see when I'm marking students' work is students get the colour change the wrong way around and they go green to orange, okay? So just be careful. Such a simple little mistake, and it, you know, obviously costs marks and general stuff. And then we'll go into actual alcohols now, okay? Right. So there's going to be a lot of me rubbing this board, obviously, because I can only fit so much onto it. So apologies for the sort of waiting around for that. Right, okay. Right. So we'll just break it down into the different types of alcohol. So the first thing we'll do is primary alcohols. Okay, so I'm going to use ethanol just to illustrate this. So CH3, CH2OH. I won't bother with displayed formula. I'm just going to use structural and skeletal to save a bit of time. Right, so it's a primary alcohol because that carbon, that's the OH carbon, bonded to one other carbon, okay? So if you put that in with an oxidizing agent, obviously you need heat. That will oxidize, first of all, to an aldehyde. So you'll get CH3, so that doesn't change. The functional group, CH2OH, changes to CHO. CHO is the way I remember that, okay? That's your aldehyde, and you get a water molecule produced in that reaction, okay? Obviously it's going to go from orange to green as the reaction takes place. Skeletal formula, CH3CH2OH plus O, heat, CH3, C, there's an H on there, O, H2O, okay? So that's the first part of this. I'll come on to reflux and distillation in a minute. Okay, now the aldehyde, so this is ethanol. That's ethanol. That can be oxidized as well, okay? So if you then took your ethanol, CH3CHO, and you expose that to the oxidizing agent, obviously you still need heat. The ethanol is going to oxidize to the carboxylic acid, so CH3CO. You don't get water in this second oxidation, okay? So that's the second oxidation, okay? So that's ethanoic acid. So skeletal formula looks like this. And that's it. Okay, so first oxidation is primary alcohol to aldehyde. Second oxidation is aldehyde to carboxylic acid. Things to remember: you only get water formed in the first oxidation, not in the second oxidation. Okay, so what if we wanted to make just the aldehyde? Okay, so if the aldehyde was wanted, what you would do is you would use, I just hold that, hopefully you can see that okay. So your primary alcohol, your ethanol, and your oxidizing agent, I'll just get something to hold this on. Okay. So your primary alcohol and your oxidizing agent are in this flask. You're heating it up, and this reaction's taking place. So the aldehyde vapor travels up here, and then you can see the way the condenser's set, the vapor can travel down this central tube of the condenser, and because you've got cold water running around the outside of the condenser, it'll cool the vapor back down, it'll condense it back into a liquid, and so the aldehyde is going to sort of liquefy and run down under gravity, run down, and it'll fall into that beaker there, okay, that collection vessel there. Okay, so by having it under distillation, you're basically taking your volatile product away from the heat source and the oxidizing agent, so you only get that one oxidation. So distillation gives you the aldehyde. Okay. If you wanted to make the carboxylic acid, you would use reflux. You would heat under reflux. An agent's in there. You heat it up. This reaction takes place. So your aldehyde vaporizes and it travels up the condenser. But because obviously you've got the cold water running around the outside, it condenses and gravity takes it back down into that flask where there's oxidizing agent and heat. And so the second oxidation takes place, and what will eventually be in there is the carboxylic acid. So both oxidations take place if you reflux it. Okay, so we'll just put that there. So distillation for aldehyde and reflux for carboxylic acid. So the only extra thing I'm going to put on this part of the board is the equation for the refluxing process, because you've got like both oxidations happening one after the next. So the equation for that, using ethanol as the example, CH3, CH2OH, 2 moles of oxidizing agent because 2 oxidations have happened, aldehyde, then carboxylic acid. That takes you to the carboxylic acid, but remember, only water is formed in the first oxidation, not in the second one. So that's the overall equation there for that. Right, I can see lots of things popping up in the chat, so I'm just going to have a look and see what it says. Right, okay, so questions wise, is it better to say tertiary alcohols aren't oxidized or they're not easily oxidized? OCR will accept they are not oxidized, okay, so I would just say that. Obviously someone said it depends on your spec, so you need to check your specification, but OCR not oxidized. Am I only doing AS content at the moment? Yes, because A2 exams have been cancelled. Once we know what's happening with the exams for the year 13 students. Some of my students might want to take the exam after the summer holidays if they're not happy with the grade that they get. So obviously I'm going to be working on A2 content, but I'm not going to do it until near the time. 2 hydroxyl groups is a diol, yeah, that's right. Not sure about 3, it's called a triol. Yeah, glycerol, someone's saying. Triol, glycerol is propane 1,2,3 triol. Allery chemistry, is he doing stuff as well today? Right, okay. Someone's asking, if you have a diol, would you form an aldehyde or ketone with 2 CO double bonds? It doesn't, it depends on what kind of OH group it is. I'll show you that now, I suppose, while we're on with this. Actually, let me finish secondary alcohols first, and then we'll bring in a diol, okay? And we'll see what happens there. Okay. Right, secondary alcohols. Okay, so the example I'm using here is propan-2-ol. So e.g. propan-2-ol. Okay, so we've got, that's CH3, CHOH, CH3, plus oxidizing agent. Obviously we need heat. And basically, there's your functional group there. That's going to change into a ketone. So you get CH3, CO, CH3, and you get a water molecule, okay? Orange to green colour change. If you do skeletal formula, so that looks like that. So the ketone, propanone, looks like that. And water, okay? And that's it, okay? So you can't oxidize the ketone, so that the reaction stops at that, okay? So we'll just write there, ketones, not oxidized. And so really all you need is a source of heat. So you could do this in a test tube, in a hot water bath. You could use distillation, you could use reflux. Typically, you would do it under reflux, so that if any alcohol evaporates with the ketone that's formed, because you could lose some alcohol, it'll just drop back down and you're making sure that it all gets oxidized. So reflux is typically used for this one. Okay. Makes sure all the alcohol reacts. Okay, and that's that. And then tertiary, just very quickly, so if I just quickly draw a tertiary alcohol, so let's make that the OH carbon, we need 3 carbons on there. So we'll just make these methyl groups. Like that, okay? So you can see that these aren't oxidized, and the reason is because there's no hydrogen on this carbon, okay? So you can see, well, you can't see it on the skeletal formula, but on the other 2, you've had hydrogens on the OH carbon that you've been able to oxidize. That doesn't have a hydrogen on that carbon, so you can't form the water molecule, basically, okay? So that's why they're not oxidized, okay? So we'll just say no H on OH carbon that can be oxidized to water, okay? And that's tertiary. I'll just quickly check the questions. Okay. No questions there, right? Right. So let's make a slightly more complicated alcohol. Let's go for 1, 2, 3, 4. I'm completely making this up, by the way. Okay, so let's put an OH there and an OH there. Okay. Right. So what we've got in here, this is a diol. It's got 1, 2, 3, 4 carbons, so it's bute. And we've got OH groups on carbon number 1, 2, 3. So this will be called butane 1,3 diol. Butane 1,3 diol. Now, you can't classify this as being primary or secondary because it's got both types of groups in, so you would classify particular OH groups, okay? So that's primary, that's secondary, okay? So this one here is primary because that carbon is only directly bonded to that one, because it's bonded to that one and that one. That's the secondary, okay? So let's oxidize this. Well, let's do both. Let's do it under distillation first, okay? So oxidize under distillation. So I'm going to treat this like a lesson now. I'm going to give you, what, 30 seconds just to think about what would form if that was oxidized under distillation, and then I'm going to do reflux as well, so I'll give you a little bit of time to think about that. If you want to think about the equation as well, we'll look at that as well. Oxidize under reflux. Okay, so we'll do both types. Okay, it's a shame that there seems to be quite a bit of a lag on the or delay on me asking a question and then something coming back. Otherwise, I would fire questions out, and if the internet was fast enough, I would just get an answer straight back, which would be better. Okay, so distillation first. So really, what I would be thinking there is that's only going to affect the primary. That's only going to sort of mean anything for the primary alcohol. Okay. So distillation, the primary alcohol will go to an aldehyde. The secondary alcohol will go to a ketone. They always go to ketones. Okay? So what's that product going to look like? We'll sort of make the equation backwards, if you like. Okay? So we've got 4 carbons. Let's just do that bit. 1, 2, 3, 4. The primary alcohol is going to go to an aldehyde because we've done distillation. So there's that bit. The secondary alcohol is going to go to a ketone. So that's that bit. And then we just the hydrogens just go on the rest. Obviously leave that, there's no hydrogen there. Okay. how many waters are going to form? Well, when that gets oxidized to an aldehyde, you get a water molecule. When that gets oxidized to a ketone, you get a water molecule. So we're going to get 2 water molecules. How many oxidizing agents do we need? Well, one oxidation's taking place there, one's taken there. So we need 2 moles of oxidizing agent. And then I'm just going to write alcohol if you don't mind. Alcohol. Can't spell. Okay? It's terrible. Sorry about that. So that would be if it was under distillation. If it was under reflux, again, you're only worried about, it's only the primary alcohol that you need to worry about. So if it's under reflux, this primary alcohol is going to turn into a carboxylic acid. The secondary alcohol still just goes to ketone. Okay? Right, so what's that going to look like? So 1, 2, 3, 4, that's now a carboxylic acid. Hydrogens, ketone, hydrogens. So how many water molecules are going to form? So 2 oxidations have happened there. 1 to the aldehyde, that makes water, but the aldehyde to carboxylic acid doesn't make water, so just 1 water there, 1 water there. Right, so we need 2 waters. How many oxidizing agents? 1 oxidation, 2, so 3 altogether, and alcohol. Try and spell it right this time. And that's that one, okay? Now, they do actually ask, I know OCR asks questions like that, okay, so it's kind of not your standard alcohol that you would have in your notes, but it's obviously, you just apply what's in your notes to get the answer. Okay. Oh, good. Someone's saying that this makes sense now, so that's nice to know. What functional group prioritise for the product's name? You don't need to know priority, functional group priority, but I'm pretty sure carboxylic acid is at the top. I'm trying to remember what the alternative name for a ketone is. Is it alkoxy? I'm gonna have to look that up, to be honest with you, but that would be that wouldn't be classed as a ketone because that's more important. So it would be some form of butanoic acid with something at carbon number 3. Okay. By all means, go and look it up, but I'm not going to stress too much over that. Could I go over the reflux one again? Certainly, yeah. I'll just check all the other questions if I've covered those. You wouldn't need to name that. Is that the same person or not? No, I don't think so. I'm confused. Can you go, oh dear, right. Have I gone too fast? Sorry about that. People are asking me to go through the reflux one again. All right then, so, where's my picture? Okay, while I'm doing this, if somebody wants to look up the what the alternative name, the sort of when ketones aren't priority, what that's called, and ping it in the chat, I'll try and come up with a name for it, but I've forgotten what it is. It's how long is it since it's about 40 years since I was at university, so yeah, right. So reflux. So this alcohol is in there with the oxidizing agent, okay? The oxidation takes place. The secondary alcohol bit gets oxidized to a ketone, so that bit there, okay? That's 1 oxidation's taking place to do that, and 1 water molecule's formed. The primary alcohol bit, okay, the first thing that will form will be this. So this will actually evaporate up into there. Okay, so this gets formed because that's got the aldehyde group on. It'll go up there. It'll condense because of the cold water. It'll drop back down, and then that will oxidize to that. Okay, so two oxidations take place on this bit. The first one takes you to that, the second one takes you to that. But water's only produced in that first oxidation reaction, not in the second one. And that's why we only get two waters happening here. Is that any clearer? Oxo. Ah, yes, thanks, Megan. Right. So, I'm going to take a guess on this, okay? Butanoic acid's more important. So this will be, because that's carbon number 3, that's number 1, because it's the most important functional group. So I'm going to call this 3-oxo-butanoic acid. Don't need another hyphen. Three-oxo-butanoic acid. So if somebody wants to do a quick Google search, a Google image search on that name, and fingers crossed, that picture comes up. The thing is about organic molecules, they have hundreds of names, absolutely loads of names. So anyway. Ah, Luke Steele, good lad. Yeah, it does sound awful, doesn't it? Someone's asking, why does the ketone oxidize? The ketone hasn't oxidized. It's still a ketone. Chat's gone quiet, so phew. Thank you, Megan. I wouldn't have enjoyed my Friday night if I would have been worried about that. It only shows the structure form. It looks right. Great. Well, there you go. I've learned something there. Thank you. Oxo. Well, I've remembered something. Can I rub this out? Shall we go through? Because that was going to be that's the first section. Okay, so the next bit was going to be isomerism. So happy to move on. Yeah, the image matches up. Phew. It's bad enough when students put you on the spot in a lab, in a classroom, where only you and your students are there, but this is going, like, anybody could be watching this, so I'm kind of being, yeah, a bit foolish maybe a bit foolish, putting myself out there. Right, okay. Can I move my head? Somebody's asking, am I gonna cover year 13 stuff? Well, I'm kind of making this up as I go along here. Right. What I'm going to do, my students don't know this yet, but what I'm going to do after half term, so after next week, okay, I'm going to be starting some year 13 topics with my students, okay? So I'm definitely going to do aromatic chemistry, so benzene and phenol and all that sort of thing. So I will be doing aromatic chemistry like this. So if you guys want to watch that, that's absolutely fine. I was also going to do rates of reaction, year 13 rates of reaction. So rate equations, all that sort of stuff, orders of reaction. So before the summer holidays, my plan was to have covered those 2 year 13 topics. So obviously carbonyls, someone's asking for carbonyls. I wouldn't be teaching that until September. Fingers crossed we're back at college in September, but that would be my plan. But I've quite enjoyed doing these live things, so if you want, I would do one of these, once we're back at work, I would do one of these throughout the year. I mean, I've spent a small fortune on whiteboards and model kits and stuff like that to kit out this bedroom for live stream. I may as well do them and sort of try and make it worthwhile. So yes, I will be doing them. Okay. Right. We need to crack on, otherwise I'm going to run out of. Okay. It was going to be enthalpy next week. Enthalpy next week. Okay. Right. Okay. Right, isomerism. Can I just ask a quick question, because I'm conscious of the time? Do you want me to do structural isomerism? Do you want me to go through structural isomerism, or shall we just, do you want to just go straight to stereoisomerism, EZ and stuff like that? Nothing. Right, okay. Straight to stereo. All right, okay. Right, structural, just very quickly. Don't know why I asked, sorry. So structural isomers have the same molecular formula, so the same number of atoms basically, but they have different structural formula. So same molecular formula, different structural formula, okay? So in the definitions for all of the isomers, it's all, some things the same, some things different. The same molecular formula, something's different structural formula. So for example, C4H10. Okay, so C4H10 could look like this. Okay, 1, 2, 3, 4. Just in a, I know that doesn't look very straight, but we class that as a straight chain alkane. So that's butane. Okay. So the structural formula for that is CH3, CH2, CH2, CH3, CH3, CH2, CH2, CH3, okay? However, you could also make a chain of 3 and put the 4th carbon on there like that and create a branch of carbon number 2. So that's called 2-methyl propane. Okay, so the structural formula for that, well basically you've got a carbon with a hydrogen on it, okay, I'm pointing at it now, and then around that carbon also you've got 3 CH3 groups. So I would write the structural formula for that like that, okay, CH3 3 times. So both of them are C4H10, same molecular formula. Yeah, but the structural formulas are different, and so that's what we mean by structural isomers. Okay. Okay, right. So stereoisomers, which I think more people are more interested in, because this tends to be the tricky one. Okay, stereoisomers. So, what's the same structural formula? Remember that was different last time. What's different? The spatial arrangements of the atoms, or it could be groups of atoms, okay? So we've got the same structural formula, but different spatial arrangements of atoms or groups. Okay, so if we go to butane now, so I bought these at the start of lockdown, and look, it's all still in its bag. So I literally opened them for this lesson, so I'm christening these with you. Right, okay, so butene. Okay, so hopefully you can see that's butene. We've got 1, 2, 3, 4 carbons. The double bond is between, starts at 2 and goes to 3. So this is butene, okay? Right, so what we can do with this is we can actually change it into a different molecule, okay, a different form of this molecule by swapping these two groups around or those two groups around, okay? So you only ever swap one set of groups around on the double bonds. So I'll just show you that. Okay, so I've just swapped those around. That's a different molecule or a different form of the molecule, okay? And it's all due to the fact, well, there's two conditions for EZ isomerism. You've got to have a carbon-carbon double bond, okay? So you've got to have a carbon-carbon double bond. And what's important about the carbon-carbon double bond is it can't rotate. So the pi bond, remember there's two types of lesson. The pi bond locks the atoms in position. Okay, if that was just a sigma bond, if I just pull this, pretend that's a sigma bond, then the sigma bonds can rotate, and so it doesn't matter if they're up there or down there. If that was an alkane, because the bond can rotate. However, double bonds can't rotate because of the pi bond, okay? So if we focus on the methyl groups, so the methyl group on this side is pointing up. The methyl group on this side of the double bond is pointing down. And because the double bond can't rotate, they're locked in that spatial arrangement, okay? I'll come on to how to name them in a second, because it would be easier if I just draw stuff on the board now, okay? If I just switch it back to the original molecule, right, so that's it, that was what we started with. The methyl groups, we'll just focus on them. The methyl groups are now both pointing up in the same direction, or if I held it the other way around, they're both pointing down, okay? And they're locked in that arrangement. So that's what makes them different, okay? So if we think about this, let's just, while I've got this in my hand now, the structural formula of this is CH3, CH, CH3. Okay, and I'll draw it that way because one of my students came up with a nice way to remember this. Okay, so that's that. Let's turn it into the other one. Right, okay. So, structural formula first. CH3, CH, CH3. Same structural formula. However, because of the lack of rotation of the double bond, we've now got that methyl group pointing up and that one pointing down. Okay, so they are stereoisomers. So what's the requirement, if you like, for stereoisomers? We'll name them in a second. Should have said EZ stereoisomerism, sorry. Okay. So rule number one, must have a carbon-carbon double bond. Remember, that can't rotate. Rule number two, each carbon of the carbon-carbon double bond must have different atoms or groups of atoms attached. Okay? So why can this show Z isomerism? So if we look at this carbon here of the double bond, they've obviously got a double bond, so we'll skip the first one. Right, that carbon there, what's bonded to that carbon? A methyl group and a hydrogen. They're different from each other. CH3 is different to H. So we move on to the next carbon. What's that carbon got bonded to it? A CH3 and an H. They're different to each other. So because you've got different atoms or groups of atoms on each carbon of the double bond, it will show EZ isomerism, okay? And so that's why it's possible. Just quickly show you butanene. Okay, it's 1, 2, 3, 4. Butanene can't show EZ isomerism because on that carbon of the double bond, you've got 2 hydrogens. So remember, each carbon of the double bond must have different atoms or groups attached. Well, that one does. That's got a hydrogen and an ethyl group. But that one has only got 2 hydrogens. They're the same, so it can't show the isomerism. Because basically, if you swap those round, you've still got the same molecule. That's what's happening there. Okay. So how do we name them? So we use the SIP rules. So that stands for Kahn, Ingold, Prelog. SIP for short. Okay. So what you do is you go to each carbon of the double bond. So we'll start here, and it's basically the atom that's got the highest atomic number has priority. So on this carbon here, we've basically got a hydrogen, which isn't shown on the skeletal, hydrogen, which has an atomic number of 1, versus carbon, which is an atomic number of 6. So carbon wins, carbon's got priority. So if I just put a red circle around there, that's the priority group, okay? And then if we move to this carbon, obviously it's going to be the same because you've got carbon versus hydrogen. Okay, so when the priority groups are on the same side of the double bond, okay, it comes from a German word for together, zusammen, it takes the Z name, okay? So when the priority groups are on the same side of the double bond, we call that the Z isomer. Okay, so this will be called Z-butene. In this one, priority is obviously that one and that one. They're on opposite sides of the double bond. That one's pointing up and that one's pointing down. So the German word for opposite, I hope I pronounce this right, is entgegen, which begins with an E. And so therefore, that's called E-butene. E-butene. Okay, so priority based on atomic number. Okay, and just check for questions. Okay. Yeah, a lot of people are asking about cis-trans, so I'm going to move on to that now. Now, I don't know if you're using OCR, I won't name the textbook, but the textbook's wrong, and the publishers have said it's wrong. Okay, so some textbooks base cis-trans on hydrogen. It's not to do with hydrogen. Okay, so I don't know whether you've been told that or not. But it's all about having identical groups on each of the carbons of the double bond, okay? So it's not limited to hydrogen, which some books mention, okay? So that's a bit of a I always have to tell my students that, because obviously they're working from a textbook that's got a mistake in it, which isn't great. But there you go. Mistakes do creep in, unfortunately. Right. Cis-trans. Right, I'm gonna sort of go a bit, difficultly. I'm gonna go up quite a bit, or hopefully not too much. But let's see what you make of this. So we'll talk about this sort of haloalkene, 1 bromo, 1 2 dichloro ethene. Okay. 1 bromo, 1 2 dichloroethane. Okay, so let's start. We've got 2 carbons, obviously, eth. 1 2 dichloro. Let's put the chlorines there and there. Okay, 1 2 dichloro. 1 bromo. And that's obviously a hydrogen. Okay? Right. So let's do EZ first. Let's make sure we know how EZ works. So have I drawn the E isomer or the Z isomer? Okay, have I drawn E or have I drawn Z? Okay, now typically got both answers in the chat now, and just basically somebody's asking the double bond. You've basically got 1 sigma and 1 pi. Okay, 1 sigma 1 pi. You don't have 2 pi bonds. 1 sigma 1 pi makes the double bond. Okay, let's break this down then. Let's go to this carbon. That's different to that. So what's got the highest atomic number? Bromine. So let's put a circle around. So that's got priority on that carbon there, okay? Because that's got a high proton number, atomic number, okay? Look at this carbon, okay? So the priority groups are on opposite sides of the double bond, okay? So this is the E isomer. So well done to those people who said E. There was lots of you said Z, by the way. Okay, so we'll draw the Z version. So what we need, basically, we'll put the bromine up here, and we'll put the chlorine down there. So we'll swap these two around. Let's just check. So priority, bromine beats chlorine, chlorine beats hydrogen. Okay, so that's Z. Entgegen, opposite, zusammen, together. Okay, so that's EZ sorted. Right. This can also show cis-trans because you've got 2 atoms that are the same on each of the carbons of the double bond. Okay, so basically we've got a chlorine and a chlorine. Okay, notice there's only 1 hydrogen in this, so the textbook that I use would say that can't show cis-trans, but unfortunately that's wrong. It's all to do with the fact that they're both the same. Okay. So I'll use a different colour. So I'm going to use red, okay? So we'll do square. So the identical groups will colour in with a red square, okay? So the easiest one I see is the sort of diagonally opposite one. So the trans one. So this is trans, and this one's cis. And that's how you do those. Just looked at the time, it's 4 o'clock already. I wasn't planning on keeping you this long. Or okay, shall we do another one? I don't think we'll definitely haven't got time to do any mechanisms, I'm afraid, today. So I think what I'll do is I'll do 2 videos, an OCR video, which will be really short because there's only 3 mechanisms that OCR need to know. So I'll record that and put it on YouTube. If you've subscribed, you'll get a notification, hint, hint. The AQA people, that's obviously it's going to take me longer to do that because there's 11 mechanisms, but obviously I'll just churn them out and put them on this whiteboard and record that, if that's okay with you. Okay, let's do one more. So the next one I've got is 2-chlorobutene. 2-chlorobutene. So let's just do skeletal formula. So butene first. 1, 2, 3, 4. Butene. Okay, so that's butene. 2-chloro. Okay, so the first sort of question could be, can it show EZ? Yes or no? Explain your answer. So let's look at that carbon there. Chlorine's different to methyl, so yeah, so far it can. Go to that carbon there. Methyl's different to hydrogen. So we've got a double bond and we've got different atoms or groups of atoms attached to each carbon of the double bond. So yes, this can show EZ isomerism. Okay, so which one have I drawn? Tell you what, let's make it a bit easier for ourselves. All I'm going to do is let's just make that more horizontal. Okay, so we'll put the chlorine there. Still the same. That's exactly the same as that. All I've done is just straightened it up. Okay, right. So, do you want to have a go? Is that E or is that Z? Off you go. E or Z? Got one answer in so far. Okay, 4 in, well, 3 in and 1 person say they don't know. Oh, is that Matthew Dixon? Is that you from Sunderland? Sorry if you didn't want me to give you a shout out there. I think I recognise another name in that list as well. Yay! Excellent. Sorry about the shout out. Alice, are you Sunderland as well? Okay. Hopefully Alice will confirm whether she is or she isn't Sunderland College. Right, okay, so predominantly one answer, but there were a few of the other answer. Okay, let's just take it from absolute scrap, beginnings, okay? So, priority on this carbon, chlorine versus carbon. Chlorine wins because it's got a higher proton number. So let's put a purple circle around the chlorine. Let's move on to this carbon. What's competing against what? Carbon versus hydrogen. Carbon wins because it's got a higher atomic number. Okay, so they're your priority groups. They are on the same side of the double bond. So that is Z. That's the Z isomer. Okay, so if we were to draw the E isomer, let's keep the double bond in the horizontal position. So let's flip these two round. So that's your chlorine. We can only swap one side around. If we do both, you're not changing the molecule. Okay? Let's put the circles on. Priority. Oops. Priority. Opposite sides of the double bond. E. Okay? So the next question is, can this show cis-trans? Yes or no? A reason would be great. If you can come up with a reason, that would be absolutely excellent. Can it show cis-trans? Oh, sorry, Alice. There must be two. There's bound to be more than one Alice Hutchins in the world. So can it show cis-trans? That's basically all I'm asking. Yes or no? If it can, why? So if somebody's saying no. 2 no's now. That's brilliant to hear. Somebody's just saying they're much clearer about E and Z isomers. You're welcome. Going to sound like a big head here, but somebody messaged me the other day and said they got 100% on a spectroscopy test after the stuff that we've been doing in on these live streams. So that was absolutely fantastic. If that person's out there, thank you for letting me know, because you made my day saying that. It's a no, right? So we've got 3 no's. Okay. I'm afraid the answer is yes, it can. Okay. So why can this show cis-trans? What's this? A methyl group. What's this? A methyl group. And so you've got the same group on each carbon of the double bond. So it can show cis-trans. Okay, so I'll just put the squares round. So that's the identical groups are opposite each other, diagonally opposite, so it's trans, cis. Okay, I just want to do one more, okay? Okay, let's just, I won't bother with cis-trans on this one, so we'll go that, okay. This can show EZ, by the way, can show cis-trans as well, actually. Okay. Right. Someone's asking, is it okay to just say EZ and not bother? I would, unless you're asked about cis-trans, I wouldn't even bother talking about cis-trans. Cis-trans is a special type of EZ, so if it can show cis-trans, it does already show EZ. I think EZ's much easier to spot, okay, than cis-trans. And I think because of all the confusion from the exam boards messing the textbooks up, they're probably not going to ask about it, okay? But don't hold me to that, because they might. But so only go down, I would personally only go down the cis-trans naming route if they ask you to do that, okay? Don't, just in case you're not sure about it, okay? Right. Right, okay. So, basically, it's what do you do? Because if you see here, you've got, it's easy to see priority on this one, okay? So that's obviously beats, that carbon beats that hydrogen there. Okay, so that's the priority group on this carbon, okay? If we go to this carbon, you've got a carbon there, and you've got a carbon there, all right? So basically, you've got identical atoms directly attached to the carbon of the double bond. So what would you then do? You look at what's bonded to that, okay? So it's called finding the first point of difference, all right? So that carbon's got 3 hydrogens on it. 1, 2, 3, okay? Whereas that carbon's it's got 2 hydrogens and then another carbon, okay? So because of that carbon there, that beats the sort of hydrogen. So the first point of difference, if you like, is they're both CH2, but then that's like CH2 with an H on, that's CH2 with a carbon on. So that group takes priority over a methyl group, okay? So that's got priority. So what I've drawn there is the Z form. So there's your priority group on there. That's the E form, okay? Right, now somebody's asked a question about, just want me to clarify cis and trans. I'm going to look something up, which is obviously, I'm not going to do it now, I'm going to do it and then I'll get back to you and I'll make sure that's in the next lesson, okay? But so far, what I've said, I'm totally happy with, okay? But I will check for that person just to put their mind at rest, okay? So that's that. So it's 12 minutes past 4. I honestly thought we'd get some mechanisms done as well, but we're not going to have time to do that today. So it looks like I've got 2 videos to make: OCRA mechanisms, AQA mechanisms. Oh, right, so I've got a selector fan in here. Excellent. I will do that. I will probably do that in about 10 minutes if that's okay. Nice to see somebody liking decent music. Good. Okay. Yeah, I saw the selector. I've seen him twice actually. So there you go. But I'm not going to go down. Yeah, you're welcome everybody. I've enjoyed it. Hope you have. And I will see you next Wednesday. So we'll go back to the normal format, 7 p.m. on Wednesday. And we're going to do, what was it again next Wednesday? Oh yeah, it was enthalpy. One of my favourite topics, enthalpy changes. Hess's cycles, I absolutely love them. Right, okay, great. Okay, see you later. Bye now. Enjoy your weekend. See ya.